All right. Now, hopefully it is doing that. So we said there, you can hear me, right? My mic is on, right? Hello, Shabab.
اي دكتور نسمعك.
Okay. So we said, to start from the beginning, we said we have a piece of copper originally at 305 millimeters. So that is the copper piece, the specimen that we have. Original length is 305 millimeter. And it is pulled in tension. So it is in tension. The arrows are showing that it is in tension with a stress of 276 megapascal. If the deformation is entirely elastic, so this is important to understand or notice the deformation we're seeing here, it is entirely elastic. So what is the meaning of that? If the deformation is entirely elastic, this means that we are in this zone basically, right? Before the plastic deformation takes place, we are in the elastic regime. We are here. This is the elastic regime, which means what? Which means that this curve is represented by what we refer to as Hooke's law. Hooke's law. So the Hooke's law is applicable. What is Hooke's law? It's sigma is equal to stiffness times the strain. So this is applied because it is in the elastic region. If we were not in the elastic region, then we cannot do that. We need more information in order to solve the problem. So what does it say? If the deformation is entirely elastic, what will be the resultant elongation? Elongation. So what are we asked to determine? The delta L is equal to what? Or delta, if you want that delta, it's not the stress here. So in order to solve this, basically you have the stress which we have, and you have the stress which is 276, and we are being told we are in the elastic zone, so this equation is applicable. So we basically can just say, where is the pen? We can basically say sigma is equal to stiffness times epsilon, and the amount that stiffness for the copper is basically 110 gigapascal. This is given a material property. You can get it from the table. So you substitute for the stress. You say 276 megapascals. So let's put the units in order to be consistent. Is equal to the stiffness, which is 110. I said it's gigapascal here, so we need to convert that in order to be consistent with this. So we will say what times 1 times 10 to the 3, so that's multiplied by 1000 times the strain, which is the delta L over L naught. How much is the L naught? We said that it is originally, its original length is 305, so that's why we will say here 305, and the unit will be in millimeter. So the result of this, since millimeter over millimeter, so the result of delta L will be in millimeter. So if you find the delta L, do the calculation. Delta L will equal to 0.77 units will be millimeter. Just calculate that using the calculator, and the unit, the delta L, you can determine by that. Very simple equation, direct problem, direct usage of the Hooke's law in the elastic region with the information that you are given. Any question? Any question, guys? Are you with me? I need somebody to answer, please. Shabab, nobody's answering me. All you guys.
هلا
وياك
دكتور.
دكتور.
وياي تسمعوني يعني ردوا علي علشان اعرف ان I'm connected يعني. Okay, so let's go to the second problem. we have another problem here. And this problem, let's read out together the problem, please. في كان عندكم سؤال على السؤال الأولي أول شيء؟ Any question here? This is a direct question.
دايركت نعم واضح.
واضح. طيب, let's go to the other problem. This is a tensile stress. So a tensile stress is applied along the long axis of a cylindrical brass. So the material we have in this case is a brass. So again, we have the same thing. The material is different, so it is cylindrical again. Again, we have tensile stress which is applied in the of course this should be more straight. I'm not that professional. A cylindrical brass rod, so that's the rod that has a diameter of 10 millimeters. So the original diameter is equal to 10 millimeters. Oops. Okay. It says determine the magnitude of the load required to produce 2.5 times 10 to the minus 3 millimeter change in the diameter. So we are being told also that the change in diameter which is required is 2.5 times 10 to the minus 3 millimeter. So how much that load should be, the force should be, how much force I should apply to this specimen of a brass in order to cause a change in the diameter of 2.5 times 10 to the minus 3 millimeters. So how can we solve this problem? Of course, we know that the brass and the copper, brass is a copper alloy, so we will take the value of E equals to 110 gigapascal in the same way. We also will take properties like Poisson's ratio to be 0.33. Nearly it is that much. So basically, what can we do to determine the force that we can get? So we are assuming that the tensile stress which is applied is in the elastic region. So we can use the Hooke's law. The stress is equal to the stiffness times the strain. So that is the stress. That is the stiffness which we already have, and this is the strain. From this, actually, we can say what the load is. So that is force divided by original area. Original area we have because we have the original diameter. So we can say that this is 110, that value we have. Also, we always use megapascal units, so we multiply by that. And the strain basically there is equal to what? The strain. Well, the strain. How much that strain is, we don't know for now. Let's see. What else can we use? We can also use Poisson's ratio relationship. We can say Poisson's ratio is equal to what? Minus strain, the lateral strain, divided by axial strain. So where is the axial strain? This is basically the axial strain, because this is axial stress and that is axial strain. So you have the lateral strain divided by the axial strain. If we know the Poisson's ratio here, and we know how much the lateral strain is, we can determine the axial strain. Do we know the lateral strain? Yes, we do. This is 0.33. The Poisson's ratio is equal to, the lateral strain is equal to, in the dimension, on the lateral dimension, which is equal to delta D divided by the original dimension, and this is the axial strain. So from this equation number 1, you can determine the value of the axial strain. You just plug the values there. So basically, let's continue that. 0.33 is equal to epsilon axial, and the delta D is equal to 2.5 10 to the minus 3, and that is in millimeters, divided by the original diameter, which is 10. So millimeter, and that is also millimeter. I don't have space here. Okay, so the only unknown in this equation will be the epsilon axial. If you get the epsilon axial here, then you can just come and substitute here. Just plug the numbers that you have here, plug the numbers here in the calculator, and put the axial strain here and put this here. You will get the axial strain. Once you get the axial strain, you substitute the axial strain in this equation, and so that is known. That is known. This number is known. The area will equal to pi over 4 d naught square. You can get it by that, and the d naught is known. That's the d naught which we have here. You can determine the original area. The only unknown in this equation will be the force. Multiply the area times this number, you will get the force which is required in order to produce 2.5 times 10 to the minus 3 millimeter change in diameter. Any question? Very clear? شباب أحتاج إلى جواب, otherwise I will understand that you're not there.
كلير دكتور.
كلير إذا وين رايحين تتغدون قاعدين يعني خلكم ويانا. Okay. Okay, if it is clear, let me go to the next issue that I want to do. Now, let's say we can have also a problem like this. Instead of having calculations like that, we can have a problem that we have curve given to us. For example, the stress strain diagram. This is not very nice stress diagram given to us. I can use another figure. I wanted to use another figure, but anyways, this is good. For example, for the tensile stress strain behavior for the brass specimen shown in figure, whatever figure which is given after this, determine the following. It says, for example, first of all, determine the modulus of elasticity. It requires the yield strength at an offset stress strain of 0.002. I don't have to tell you that. I can just ask you, determine the yield strength of the material. You need to understand which one you want to get. The maximum load that can be sustained with a cylindrical specimen original diameter is this much. The change in the length of the specimen originally this much long, that is subjected to a tensile stress of that much. So let us look at the figure. If we look at the figure, of course this sub-figure which is given here is part of the figure in order to show the elastic deformation more. So when it comes to determining the stiffness of the material, the stiffness of the material would be what? Okay. The stiffness of the material would be basically, you need to choose 2 points. Let's say this point is 10 and 0.001, and choose another point, for example 30 in the same curve. 30 is nearly 0.002. So therefore you can determine that's the triangle hopefully there. So from that you can determine the slope of that line, and the slope of that line is is basically here, and the slope of that line is basically delta y over delta x if you want, delta x, or you can say delta sigma over delta epsilon. So you can determine that. Once you get both the numbers there, this number you have, that number you have, you can plug into this equation and get the stiffness of the material, which is the slope of the line. If you want to get another thing, which is the yield strength, so this is the yield strength. It says at 0.002. This is 0.002. That is 0.002 there. That is 0.002. I don't know why is this happening. Let's see. So from that, sorry, this is 0.002, which we have. This is 0.001. This is 0.002. It says from 0.002. How we determine, since this is not a double yield phenomena here, so you can go to 0.002 and extend the line, which is parallel. Basically, this line is parallel to the elastic regime, and when it intersects, wherever it intersects the curve of the line, then you do the reading there and say this is my 0.002 yield strength. So here the value is the 0.002 to yield strength. Okay, so that is the yield strength that you could get. If we had the upper and lower behavior, then obviously we just go to the low. This is the upper yield strength. This is the lower yield strength. So this is the lower yield. And that will be the sigma yield. We could do it this way. Another thing that we could be asked for is the UTS. The UTS, or you can say also the tensile strength. The tensile strength of the material will be the maximum stress in the material. Basically, if you look at this curve, the maximum will be somewhere else, somewhere there. And this point, if you read it on the curve there, it will give you 450 megapascals. Another thing which we could be asked is that this is what is being mentioned here. It says, what's the maximum load that can be sustained on a cylindrical specimen with the original diameter of this much? So basically, original diameter is being, you're saying that here the D naught is equal to 12.8 millimeter. It says, what is the load? Basically, you can say the stress is equal to force over the area, original area, and that original area is pi over 4, 12.8 square. You can get that. The stress which we are looking at, when we say the maximum load that could be sustained, then you will be using the UTS, which is this value. If you use this value there, so that will be 450, and that is in megapascals. So you can determine the force then therefore from this equation. So this is how you could be doing it. The change in the length of a specimen, originally 250 millimeter. So originally we have the original length, we are being told, is equal to 250 millimeter. It says, what is the change in the length if the material is subjected to a tensile stress of 345? Our stress is equal to 345 megapascal. Notice we are not being told anything about if this is in the elastic zone or if it is in the elastic zone or not. So we need to search where does this fall. If this is basically if this is 450, this will be 400 and this is 300. صح? Because this is 100. If we say this is 100, depends. I might be wrong. You can look at what I'm doing. And this is 300. So this is 400. This is basically 450. And looking at this stress, you can see that this stress is beyond that 300. 345 is nearly there. That is nearly 345 and very close to 350. So basically, if that is the stress that we are looking at, we are not in the elastic zone. And if we are not in the elastic zone, we cannot use the Hooke's law. We cannot use the equation sigma is equal to epsilon to stiffness times epsilon. That equation that equation we cannot use anymore. Why? Because we are in the plastic zone. So what do we do then? Well, you read the curve from where it is. You read the curve from here. You have I'm not sure about that, but you make a straight line, it intersects there, and drop a vertical from here to there using the ruler, and then there you will determine the value of the strain. So you have the strain here. If you have the value of the strain from there, strain is equal to delta L over L original. L original you have, which is 250 millimeter. The strain you determined from here, you can determine the delta L of the material. So I'm giving you both cases. Like the first case where you can use the Hooke's law and determine the value of the changes from the Hooke's law, and the second case where you cannot use the Hooke's law because you are in the plastic zone. Since you are in the plastic zone, you can use you can use a different formula which can, like Holloman's rule, or you can use the curve itself, as you can see, intersect at that point and get the values of the strain. Any question? I guess not. Very simple. It is simple, I know. Let's go to the last problem that we want to look at. It says an aluminium alloy, which we have seen, has a final gauge length after failure of this much. So this is the final gauge length. And final, that's the L final. Inch. And a final diameter, that is the diameter, the final diameter after the failure has occurred. So what happened here in this question is that we took the specimen, we have a specimen, and this specimen, what did we do with it? We have a specimen, we have the specimen, and that specimen, we measured the dimensions of the specimen. Before doing the test, we took the initial dimensions there, we took the initial length, and we took the initial diameter as well. And then after doing the test, after the test was went through fracture, actually, you had that cup cone failure, if you remember. So this is a tensile failure, مثلا. Then when this happened, we put it together like that. Maybe we'll use a pen for this. Once this happened, we put it together and take the final length there, from here to there. That's the final length. And that's the L final. And we take that dimension, the smallest dimension there, to be the final diameter. So this is what we have done. It says now calculate the ductility of this alloy. How can we calculate the ductility? Well, ductility, we have two formulas. We have the percent elongation and we have the percent reduction in area. The percent elongation will be the final length minus initial length over initial length times 100. So this is a calculation of ductility. The final length will be 2.195, that's the final length. The initial length was 2, so 2.15 minus 2 divided by 2 divided by the initial length times 100, that is 9.75. Or we could calculate it using the reduction in area. Normally people use the percent elongation. It's the initial area minus the final area over initial area. You can see times 100. So you can see it is 5/4. That's the final dimension which we are having. That's the initial dimension that we are having. Why initial? Because the initial normally is larger than the because this is lateral change actually. So the final is smaller than the initial one. So we say the initial area, that's the initial diameter, minus the final area over the final area which we are having, or initial area, sorry, which we are having here. Multiplied by 100, we get it 37.8. When we did this calculation, obviously, I have told you that the values of the percent elongation and percent reduction of area will not be the same. And as you could see, they are not the same after large or excessive deformation that could take place. So this is how we calculate the percent elongation, both in terms of the ductility, sorry, both in terms of percent elongation and or percent reduction in area. I just wanted today to do such a problems with you, and then I will next week we will do maybe the last lab and give you some assignments. I see most of the students are not with us today, so next week we will do some other exercise in the lab time. Maybe we will start on Sunday or Monday. I will tell you that beforehand, and we will do some job I will give you to do before you start your tests. But for now, this is what I thought you might need to do calculations. That's why I wanted to do those problems with you in the lab today. Any questions, guys?
Thank you so much, Doctor.
Okay, then. If there are no questions, then I will stop the recording here first.